All right, what's going on, y'all? This one's the last 3D problem I do. We have to find nodal displacements, stresses, and we got to verify force equilibrium at node 1. They give us E and A for every element. They don't give us lengths, but we have to find them. Not that big of a deal. All supports are ball and socket, so that means nodes 2, 3, 4, and 5. They're fixed in the XYZ direction, so they're going to save us a lot of time in that sense. But you know what, let's go ahead and get started. This one is pretty long, and we verify forces equilibrium at node 1, so it's really important that you watch that part. I don't do it in any other video, and I'm not going to do it in any future videos. There is a problem 341. If you guys want me to, I will do it, but as of now, I'll just kind of keep going with the course. There's a lot more things to cover, but let's go ahead and get started. All right, so again, right, the main goal for these 3D problems is trying to find the stiffness matrix for each element. In this case, we have 4, so it's going to be a 15 by 15, right? There's 5 nodes. Multiply it by the XYZ direction, that's 3. 5 times 3, that's 15. But each little element is going to have a 6 by 6 matrix that we're later going to combine to make the global stiffness matrix, just like we've been doing with 2D problems, right? So in this case, it is a pretty huge table, but because there's a lot of fixed supports, a lot of these will cancel out, so you'll see what I mean. But before we get the stiffness, obviously we need EA over L for each element. Now they give us E for all of them, they give us A for all of them, but L changes. Now to get L for 3D elements, and I've noticed it's been the case with all 3D problems, they're never going to straight up give them to you. You just use the distance formula from algebra or calculus, I can't remember, but it's just a change in x from the final. Well, it doesn't really matter, right, because you square it, but I always like to stick to final minus initial. And yeah, that's pretty much it. So we go ahead and find these values right here. So for the first one, it's a final minus initial. In all cases, we're going to be going from the smallest node to the biggest. So for element 1, we're going to go from node 1 to 2. Then we're going to go from 1 to 3, 1 to 4, and 1 to 5. So if you do that, that's going to be start at 2, go to 4. The change in x is 0 minus 4. That's negative 4 squared. And then 4 minus 4, that is 0 squared. And then finally 0, the z coordinates, right? 0 minus 3, that is negative 3 squared. Let's go ahead and we'll do the math later, right? Let's just go ahead and do the rest. For element 2 now, we are going from 1 to 3, so that's 3 minus 1. So it's 0 minus 4, negative 4 squared, plus 4 minus 4, which is 0 squared, plus 6 minus 3, positive 3 squared. And then next one, 4 minus 4, that is 0 squared, plus 0 minus 4, it's negative 4 squared, plus 3 minus 3, that's 0 squared. And finally, L4, it's 8 minus 4 for the x, so that is 4 squared plus negative 1 minus 4, that is negative 5 squared plus 1 minus 3, that's negative 2 squared. And if you do the math for all of them, you'll get 5 meters for L1, 5 meters for L2, 4 meters for L3, and 6.71, that's a 6 meters for L4. And they're in meters because it says right here, all supports, the coordinates of each node in meters are shown in the figure. So we're going to want to stick with newtons and meters. Keep it simple, okay? No kilonewtons, none of that. So it's going to be 10,000, not 10. Just FYI. So now that we have L's, we could go ahead and find EA over L. So it's easy, right? It's 210 times 10 to the 9 gigapascals. And again, a pascal is a newton per meter squared. That's exactly what we want, remember? So this is 10 to the 9 times 210 times, it's multiplied to area, so times 10 times 10 to the negative 4. It's in meters squared. So, and then we divide by L, meters. So all the units line up. If you do that for element 1, you will get 4.2 times 10 to the 7. I move make sure you know how to work with decimals, right? It was 10 to the 9 here, 10 to the negative 4 here, that's 10 to the 5th. But I moved the decimal to make it 10 to the 7. I'm pretty sure you should know how to do that by now, right? Same thing, since the same length for element 2, so it's the same EA over L, right? Because EA is the same for all of them, so it's just 4.2 times 10 to the 7. Then for element 3, we will get 5.25 times 10 to the 7. And finally for element 4, we'll get 3.13 times 10 to the 7. Now we're also going to need E over L because the problem says solve for stresses, and the equation for stresses was right here, if you remember. It's negative CX, negative CY, negative CZ, but you multiply all this pretty much by E over L. I'll cover this later. Just you need that E over L. Okay. So let's go ahead and do that. It's the same thing. It's the same numbers in magnitude. It's just that now we didn't count area, so it's 10 to the negative 3, right? So we just add a 10 to the 3 here. That's going to be 4.2 times 10 to the 10. 4.2 times 10 to the 10. 5.25 times 10 to the 10. And 3.13 times 10 to the 10. It's just a difference by 10 to the 3, and it's positive, not negative, because in this case, when you multiplied the E over L in this case by area, it made it smaller. But now that we're not doing it, it's going to make it bigger. So it's 10 to the 10, not 10 to the 7. But I mean, that's pretty simple math, right? Just do E over L. Just 210 times 10 to the 9 divided by 5, and etc. for all of them. So now that we got that, so we're doing direction of cosines now. Now, if you remember in 2D, we use angles. You remember? We get the angle, then we get the cosine, then the sine, then cosine squared, cosine times sine, all that good stuff. Now, you can't use angles here in 3D because it's a little bit more complicated to see, right? But direction of cosines it's the same thing. So you know how cosine of theta is equal to adjacent over hypotenuse? That's all it is. You could either use the angle, or you could just do A over H, and that's exactly what they're doing. So they're getting the X component, dividing it by the hypotenuse, they're getting the Y component divided by the hypotenuse, and then the Z divided by hypotenuse, and that's all it is. So it's pretty much the same thing if you really think about it, but just follow the formulas, you'll be all right. Use these formulas, CX, CY, CZ. You fill it up here, then you square them, then you kind of multiply each other. That's all it is. Okay, so let's go ahead and do that. So for the first element, for element 1, we're going from nodes 1 to 2, okay? So when you do that, you do final minus initial, x final minus x initial. So it's 0 minus 4, so it's negative 4, divided by the length of element 1, that's 5. Negative 4 over 5, that is negative 0.8. For the y1, you do 4 minus 4, which is 0, divided by length is 0, right? Then for the z, 0 minus 3, that's negative 3 divided by 5, okay? That is negative 0.6. And we could go ahead and fill in the rest of the tables, right? So cx squared, that's 0.64, cy squared is 0, cz squared is 0.36. I'm just squaring these to here. And then cx times cy, that is positive 0. Oh, I'm sorry. Anything with a cy is 0. Okay, so that's a 0, that's a 0, and then cx times cz, that's positive 0.48. Okay, cool, so we got that. Next one, so now we're doing element 2. That goes from 1 to 3. We always go from the smallest node to the biggest node. And just FYI, that's not going to mess you up when you do the global stiffness matrix, but it will mess you up when we get to the stresses, and I'll explain why. If you saw the other videos, you know why. But so now let's go ahead and do the x component for the second element. So it's 0, final minus initial, right? 0 minus 4, that is negative 4 divided by 5, another negative 0.8. cy, it's 4 minus 4, that's 0 divided by the length is 0. cz now, zf, which is 6, minus zi, which is 3, that's 3 divided by 5. That is positive 0.6. So when you square these, you'll get the same numbers as the top one, right? Because, I mean, when you square them, the negatives go away. But, and cy is also 0, so anything with a cy here, that's 0, 0. cx times cz, it's a negative 0.48. Okay? And that's it. Next element is going from 1 to 4. So final minus initial, 4 coordinates minus 1 coordinates. So it's 4 minus 4. For the x one, that's 0. For the y one, it's 0 minus 4, negative 4, divided by the length now, 4. That's negative 1. Z, 3 minus 3, that's 0. Square them, 0, 1, 0. Anything with all these are going to be 0. 0, 0, 0, because CX and CZ are 0. So CX is here, CZ is here, CX, CZ. It's all 0. Finally, this one goes from 1 to 5, right? Nodes 1 to 5. We always start from the smallest node to the biggest. So all these coordinates minus all these coordinates. 8 minus 4, that's a positive 4, divided by 6.71. That is a 0.6. Next one, right, we're going to do negative 1 minus 4, that's negative 5, divided by 6.71. That is negative 0.75. And then if you do the z components, 1 minus 3 divided by 6.71, you will get negative 0.3. Now, if you go ahead and square these numbers just like we've been doing, right, you'll get positive 0.36. You will get 0.56 for this one, and then you will get 0.09. Okay, then do cx times cy, you will get negative 0.45, 0.23, and negative 0.18. All right, go ahead and verify those numbers. They are correct, but you should always do it yourself just to make sure. Now we're gonna go ahead and start doing the stiffness matrices, right? Remember, I told you we will want this 6x6 matrix for each element. That's exactly what we're gonna do. So the formula is K is equal to the stiffness, EA over L, that we got here, times the matrix. Now, we'll get there, hold on. So for the first one, K1, that is element 1, right? We're element 1. It's 4.2 times 10 to the 7. There we go. They're all 10 to the 7, so I just kind of already threw them in there. K2 is going to be 4.2 as well, times 10 to the 7. Okay. K3 is going to be 5.25 times 10 to the 7. And finally, 3.13 for element 4. It's going to be here. 3.13 times 10 to the 7. Okay. Now, let's go ahead and do that. The nodes, right? What's going to be on the side, on the bottom? In this case, I just gave it dummy variables, U1, U2, right? From nodes 1 to 2, and then from 1 to 2 this way. Now, it's the same thing. So for first element, we went from 1 to 2, so that's the exact order we're going to put them in. We're going to go U1, V1, W1, XYZ, then U2, V2, W2. And same across, U1, V1, W1, U2, V2, W2. So that's the first one. For the second one, we're going from 1 to 3. So we're going now, let me just make sure you can see it right there. So we're going U1, V1, W1, U3, V3, W3. Same thing here, U1, V1, W1, U3, V3, W3. That's a 3. Finally, or not finally, I'm sorry. Next one, element 3 now is going from nodes 1 to 4. So we go U1, V1, W1. Then we got U4. Yeah, U4. U4, V4, W4. This one goes U1, V1. I'm just repeating it, right? U1, U4, V4, W4. And finally, the last one goes from nodes 1 to 5. So we're going to start at U1, V1, W1, U5, V5, W5. All right, now we'll go ahead and start filling in the matrix. So look, for each matrix, let's do element 1 first, okay? Now make sure you can see the paper right there. So we will need cx squared, cy squared, cz squared, cx squared, cy squared, cz squared, then cxy, cyz, and then cxz here, and it's all symmetrical, okay? The only reason I didn't continue going down is because I got lost. This negative cxy is here, this negative cxz is here, so it just went down like that, right? Point is, we have all these numbers, right? We have cx squared, cy squared, cz squared, these three, cxy, cyz, and cxz, they're over here. And after that is just pretty much following the table and filling it in, but that's a lot of writing, okay? It's better to apply your boundary conditions right now to save yourself on that writing. So we know the boundary conditions, u2, v2, and w2 is equal to 0. u3, v3, and w3 is equal to 0. u4, v4, w4 is equal to 0, and u5, v5, w5 is equal to 0. Well, why did I say they're equal to 0? Because they're ball and socket joints. They prevent translation in the x, y, and z direction. They can only like rotate, you know, like a shoulder. Your shoulder can't go in the z, x, or y direction, but you could like twist it, you know? Same thing here. So what happens is that since translation is fixed, there's 0. u1, v1, what I just said, right? Not u1, I'm sorry. u1, v1, and w1 is the only one that could move up, down, left, right, side to side. So that is not 0. We can't cross those out, but the rest are. So we'll go ahead and do that, right? This is gone, 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 this is gone right here, this is gone, this is gone, and oh snap, I didn't do these. u1, v1, w1, u5, v5, w5, and these are gone. Nodes 2, 3, 4, and 5 are gone. Okay, and same thing across. So that saves us a ton of writing, right? I'll show you what we just did in a second. Let me just finish crossing them out, but we saved ourselves a ton of filling in. Now we only have to fill in what, 25% of the work. All these are gone. Let me just finish this up. Looks a little sloppy when I go fast, but doesn't matter. Okay. And that one. So check it out. We only care about these 9 positions here, these 9 positions here, 9 here, 9 here, because u1 and v1 and w1 are not canceled out. There's going to be displacement at that node, and that's exactly what we're going to find. Okay, so check this out now. So on this 6x6 matrix, for this specific case, we canceled out these 3 and these 3 like this. So we only care about this one right here. So we care about cx squared, cy squared, cz squared for element 1, right? We're doing element 1. So let's go ahead and do that. 0.64, 0, 0.36. So 0.64, 0, 0.36. I'm following this one, and this one. Now the next one, cxy, cxcy, cycz. So it's these two, 0 and 0, 0, 0. And then finally cxcz up here, which is 0.48 for element 1, okay? That's what we're doing, 0.48. It's symmetrical, so the rows become columns. That 0 goes here, 0.48 goes here, and that 0 comes here. So that one's done, okay? Now let's go ahead and do the next one. Same thing for this one. Now we're only concerned about this little block. Let's go ahead and do that. For element 3 now, you know what, let's go to element 2. Same thing though. Element 2, it's 0.64, 0.36. So it's 0.64, 0, 0.36. Next one is 0, 0, 0, 0. Then finally negative 0.48. Negative 0.48, negative. Becomes 0, negative 0.48, and 0. Symmetrical. Next one. Cx squared is 0. Cy squared is 1, cz squared 0, so it's 0, 1, 0. Cxy, cycz, and cxcz are all 0, so all these are 0. Symmetrical, so we go this way, and that's done. Next one. Finally, cx squared is 0.36 for element 4, 0.56 for element for element 4 for cy squared, and 0.09 for CZ squared. Next one's CXCY is negative 0.45, and it's 0.23. Right, I'm just following the outline here. And another thing to remember is here they're negative, okay? So if you would have canceled out U1, V1, W1 and kept these, remember to switch the signs. You got to follow this formula right here. This is really important. The book likes to call this like each matrix lambda, so it's lambda, negative lambda, negative lambda, lambda. But just wanted to point that out in case you were curious. But make sure you follow the signs here, okay? And continuing it, right? CXCZ is negative 0.18. Then we got it's symmetrical, so 0.45. Then we got negative 0.18, 0.23, and we are good. Okay, cool. Now, to get the global stiffness matrix, you have to add all the matrices. But you cannot do that unless you have the same number being multiplied to them. So we can't just add 0 plus 0.36 plus 0.64 plus 0.64, right? And I mentioned those because they're all U1, U1s. So U1, 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 U1. You add each position, okay? But you can't do that because look, this is getting multiplied by 4.2. This one's getting multiplied by 5.25, 4.2, 3.13. They're not all the same magnitude in that sense. And then obviously times 10 to the 7, right? Don't forget that. But what's more important is this one. So what I'm gonna do is I'm gonna multiply 4.2 into everything inside, multiply this 4.2 into everything inside, multiply 3.13 to everything inside, and 5.25 to everything inside. When I do that, they will all share the same magnitude now, since 10 to the 7 is the only thing outside, and then I will be able to add them. All right, so that's exactly what I did, right? I just multiplied all these numbers into the matrix, and when I do that, all these go away because you already multiplied it into the matrix, so it's already factored in. And at each matrix, you're gonna have a nice 10 to the 7 outside, and now you can add them because they all share the same common factor outside the matrix. So we could go ahead and add all U1, U1 positions, U1, V1, U1, W1, pretty much the whole matrix, right? In this case, it looks nice because you just multiply the first one on each one, boom, boom. Add them, and then same thing for all of them. Sometimes you'll have like numbers here that you have to add. You saw it in the 2D problems where you had to do that if you saw the other videos. But in this case, it's easy, pretty straightforward. So we go ahead and do that, right? So it's gonna be a 15 by 15 matrix. I have it here. You got your force vector, global stiffness matrix times your displacement vector. Now it looks scary, but just like we did here, we're gonna apply the boundary conditions, and that's gonna cancel out all of them. So let me go ahead and do that. Look, I'm gonna apply the U2 all the way to W5 boundary conditions, the same going down, and then I'm gonna go ahead and add the force numbers. Because we know at force 1x, there's no force being applied in the x direction. There's none in the z direction, just a negative 10,000. Again, we want newtons, remember, in the y direction. So that's what we're gonna do, and just give me a second. All right, so I wanna go ahead and did that, right? So now we only focused on this 9 by 9 matrix, which lines up perfectly, right, with the other ones, U1, V1, W1, U1, V1, W1. So you add all the positions to each one, U1, V1, W1, U1 here, 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 same thing. So 2.69 plus 2.69 plus 1.13 plus 0, that is going to give you, let me flip my other paper, 6.51 up here, okay? Do the next one, right? 0, 0, 0, negative 1.41. That is negative 1.41. And I'm gonna go ahead and do the rest for the remaining ones, right? You can do it on your own. I'm assuming you know how to do it by now if you made it this far. If you haven't, just watch the 2D problems, the same concept, just now it's 3D. But I mean, you're still just adding matrices. That's all it is. And you know you're kind of doing something right. I didn't notice this at first, or else I would have mentioned it in the other videos. But even this matrix is symmetrical. So negative 1.41 here, here, negative 0.56 here, here, 0.72 here, here. I didn't know that, you know, and I wish I would have known sooner. That's kind of a cool way to verify your process that you're doing it right so far. And if you do the, oh, I'm sorry, I didn't add the forces. So F1Z0, F1X is 0, and F1Y is negative 10,000. So this is 0, 0, negative 10,000. And there's a 10 to the 7 here, remember, okay? I didn't forget it, you just can't see it that good. But there's a 10 to the 7 that you cannot ignore. Now, when you do your equations, you usually, so let me go ahead and show you. I'm gonna go ahead and just give you the answers, but I'm gonna show you how to do it. So there's my other paper, right? It's the same thing. Forget all this, I'll explain this in a bit. But point is, it's 6.51 U1 minus 1.41 V1 minus 0.56 W1 is equal to 0. But you multiply it times 10 to the 7. I had it here, but what I did was I had negative 10,000 here. I just divided 10 to the 7 on both sides of the equation for all three. In this case, it just went away perfectly because it's divided by 0 and 0. But here, that negative 10,000 turned into a negative 0.001. So that means these equations were alone now, and this is how you solve these problems. This is just algebra, so you can kind of skip this part, but for those that don't know, you pick two equations. In this case, I chose the first two. You're gonna have to use all three eventually, so it doesn't matter, don't try to go the easy route. But the reason I chose 1 and 2, well, I mean, because I had to, right? This is what I did. I saw V1, it looked the simplest, right? This one looks complicated, decimals and whatnot. This one had a nice 7. So I want to go ahead and eliminated the V1. So what I did was I noticed that both V1s have negative and positive opposite signs, okay? So what you do now is you multiply by the numbers, but they're the same. In this case, they're both positive. They have to have the same sign because it's going to work out perfectly. If you multiply the top equation by 7 and the bottom equation by 1.41, you're going to get this right here. 0 is equal to some number U1, some number V1, some number U1, and then 1.41 times equation 2 is going to get you this, 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 and they cancel out perfectly. A negative with the positive, they cancel out. So we eliminated V1 and we got that, okay? Forget about this for just a second. Focus on the cloud, okay? So we got that equation. We repeated the process. We know now equations 1 and 3. The reason I chose 1 and 3 and not 2 and 3, I chose not to use 2 because it had this number. I like to stick with zeros. It's one less number we have to worry about. So equation 1, you have to eliminate the same variable, V1, okay? So now you're stuck. So multiply and notice this is positive and negative. So now what you do is you multiply the top equation by 0.72, the bottom equation by 1.41, and you'll get these numbers right here, same thing, right? V1 should cancel out if you're doing everything correctly. Positive and negative, right? So that means when you add this positive number minus this one, this negative number plus this one, you'll get this. So now what you do is you eliminate one more variable using your clouded equations. So in this case, I got rid of what? W1. So I multiplied, oh look, before I multiplied, it's a positive here and a negative here, so that means we're good. We multiply both equations by a positive number. So in this case, it was 4.25 to the top equation and 2.9 to the bottom equation. If you do that, you'll get this. Pretty much the W1s will cancel out. Something happened here. What happened? This should be a positive. Yes, it's a positive. Right here. Okay, my bad. They cancel out. And then you get this equation right here. Solve for U1. You will get U1 is equal to this. Then U1, plug it into any equation, doesn't matter. Use this one, whatever. You get W1. Now that you have U1 and W1, use one of these three equations to get V1. And boom, that's how you get those. Okay, so just wanted to explain that. It was a lot of writing, so I didn't want to do it again. But U1 is negative 0.1234 3053 meters. I don't like doing the 10 to the negative whatever. This is 10 to the negative 5. 3.053 negative, right? So negative 3.053 times 10 to the negative 5. That's all it is. 1, 2, 3, 4, 5. Yeah. V1 is negative 0.0001529 meters. And W1 is a positive 0.0002802 meters. Okay. So those are your answers for displacement. That's one part of the problem. That means we are almost there. Okay, so let's lock that up. Now let's get the stresses of each element. So the stress formula, it's this one. I wrote it down here. It's the negative values of cx, cy, and cz first, and then the positive ones. And then these are dummy numbers, right? But it's just pretty much from one node where you started. In this case, we started, remember, 1 to 2. We started at 1, going to 2. Started at 1, going to 3, 1 to 4, 1 to 5. So in this case, for the first element, right, we went from 1 to 2. So it's U1, V1, W1, U2, V2, W2. Now, if you remember, I told you that the signs, it's really important the way you determine direction. Because if you would have went from 1, in this case, we went from 1 to 2, right? So we did 2 coordinates minus 1 coordinates, right? That was a negative. It was, let's do the first one again. XF minus XI. It was 0 minus 4, which is negative 4 divided by 5. That's a negative 0.8. If you would have did the other way, that would have been a positive 0.8, okay? And if that would have been a positive, that would have switched this sign right here. It would have been a negative 0.8, and that would have given you a tension or compression value. So you'll get the same numbers in magnitude, but your compression, it will determine either compression or tension depending on the direction you chose. That's why it's really important that you do it a specific way, okay? It's real easy. It's not that hard, right? It's just if you're going in the direction from 1 to 2, now you're going to do 2 minus 1. Just be consistent. You'll be all right. This logic doesn't apply when we verify forces, but I'll get there. Relax. This is only for like the stiffness matrix up to the stress values. So let's go ahead and do that, right? E over L for sigma 1, it was 4.2 times 10 to the 10. So let's do that. 4.2 times 10 to the 10. Bracket. Negative cx, negative cy, negative cz. So the sign switch for element 1. So now it's going to be 0.8, 0, 0.6. Because the sign switched, okay? Negative, negative, negative. So 0.8, 0, 0.6. Then signs are regular, so it's negative 0.8, 0, negative 0.6. Now, your displacement vector, it's going to be, we went from nodes 1 to 2 for the first element, remember? So that's all it is. It's U1, V1, W1, U2, V2, W2. U1, V1, W1, it's right here. It's negative 0.1234, 30, 53. Negative 0.123, 15209. Then it's positive 0.1234, 2802. Then 0, 0, 0. U2, V2, and W2 were all 0. Well, everything was, remember? All of these were 0. So now, let's go ahead and do the math, right? So it's sigma 1 is equal to 4.2 times 10 to the 10, parentheses, 0.8 times this, plus 0 times the second one, plus 0.6 times this third one, plus negative 0.8 times 0, plus 0 times 0, plus negative 0.6 times 0. So fortunately, these three we don't care about because they go to 0. This 0 cancels out with the negative, so it's pretty much 0.8 times the first one, which is negative 0.123424442, and then plus 0.6 times the third one. Okay, they just kind of you kind of go like that. Okay, and then plus, what number is that? 0.1234161. Add these two numbers, multiply by 4.2, then multiply that times 10 to the 10. You will get sigma 1 is equal to negative 319,536 pascals, or Newton per meter squared, same thing. And that is in compression. Why? Because it's negative. Now, I'm not going to do the rest because it is a lot of writing, but I will explain each one just so you won't get mixed up. And I mean, it's nothing hard, right? It's just a process. So CX, CY, CZ for element 2 now, it's negative 0.8, 0, 0.6. Negative, 0, positive. So that means this is going to be a positive 0, negative, right? Because it's sign switch. So it's negative 0.8. No, I'm sorry. It's positive 0.8, 0, negative 0.6, and then it's negative 0.8, 0, positive 0.6. Now the vector, thankfully, for every element, all 4 of them, it's going to be the same because you went from 1 to 2 for the first one, nodes 1 to 3 for the second one, nodes 1 to 4 for the third element, and the last element went from nodes 1 to 5. But U2, V2, W2, U3, V3, W3, they're all going to be right here located. You always start at 1, right? And you went to the other node. So they're all going to be 0. And U1's always first in each element. So this little displacement thing is going to be the same for all of them. Finally, you do the math, right? Just like we did here. Is this one times this one, 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 this one, this one, this one, this one. Add them up and multiply that by your E over L. E over L is going to change, remember, okay? And the next one, it's also 4.2, but then it's going to be 5.25, 3.13, and that's pretty much it. Go ahead and try it. You cannot mess it up, like, for real, man. If you mess this up, I got no faith in you in this class whatsoever. No offense, man, but that's like, what do you call it? Matrix algebra. So, I mean, if you follow what I said, you'll be all right. You know what I'm saying? It's sigma 3. It's negative 7,984,725 pascals, and it's also in compression. Finally, sigma 4 is equal to negative 2,733 867 pascals, and that's in compression. So these are the numbers right here for stress. Talking about stress, man, I'm a little stressed just doing this damn problem, but it's all good. Hopefully I can help one of you guys out there. Okay, so we got this, right? This is the numbers you should get. They're all in compression. It's kind of hard to see it in 3D, but just take your numbers word for it. You'll be all right. And again, just CX, CY, CZ will change for each element. You'll be all right. Okay, just make sure you're plugging in the right numbers here. It changes for each element. Make sure the negative signs, flip them, whatever you got on the other side of the paper. E over L is going to change, and this one's going to be the same for all of them in this specific problem, okay? Just take that into account. Now we know force is equal to, so we know sigma is equal to force over area. That means force is equal to sigma times area. Now the only reason I'm finding force now is because we're going to need it to verify the forces at node 1, okay? You don't use it using stress values. You use it using force values. And that's easy, right? The area is the same for all of them, 10 times 10 to the negative 4. This number is just 10 to the negative 3 if you think about it, right? 10 to the negative 3. So what that does is that just moves each stress number 3 decimal places that way. So that means sigma 1 is negative 300 and let's put 320 newtons, okay? And that's in compression as well. That doesn't change. It's negative. F2, it's gonna be, move it 3 decimals over, it's negative 1732 newtons, and that's in compression. And F3, F4 is equal to, just move 3 decimal places over for each one. Negative 7985 newtons, and that's in compression. Finally, negative 2,734 newtons, and that's in compression. So these are your force values. You go ahead and box them. It's not really asking for them, but it's real good to have them, I guess, boxed, just so your professor thinks you're smart or some shit, right? All right, man, it's just long. Finally, we're gonna verify force equilibrium at node 1. So that one, I'm gonna pause the video here. I'm gonna continue right after, but it's real complicated, okay? It's what's complicated, but if you follow what I say, you'll be all right, okay? Just let's go ahead. All right, so this part of the video is really critical, okay? This is 340 continued. These are the notes that I want to go over with first before I start doing the problem, but we got to remember a couple things. So you remember from 2D statics, right? I'm just reading from my notes here. In 2D statics, we used angles for X and Y components of force, right? You know, if you had 500 pounds going this way at a 30-degree angle from the X-axis, and in this case, it was a bar, right? Let's assume it. It was 4 meters long, and it has 500 pounds of force being applied to it as tension. you know from trigonometry, this length here is 3.46. This length here is 2, right? Cosine and sine of 30, opposite hypotenuse, all that good stuff, whatever. Now, there's two ways you could do it in statics, if you remember. You could do 500 cosine 30 to get the x component of this force, or you could use 500 times 3.46 over 4. It's the same thing, right? Because you know how cosine of theta is equal to adjacent over hypotenuse? So it's, you either use one side of the equal sign or the other. That's all it is, right? So it's kind of the same thing that we're going to be applying here. But we're not going to use angles, because using angles, just like I told you when we were finding the other stuff here, remember? It's better to just use the adjacent values over the lengths. And that's exactly what we're going to do, so just keep that in mind. So obviously we're going to need the lengths. In this case, it was length 5 meters, 5 meters, 4 meters, and 6.71 meters, right? Just copied it over. What else? So it says, remember, compression points into the nodes and tension points away from the nodes. When you do this, the negative signs go away. We just care about magnitude. The arrows already took that into account. Another thing, remember to convert kips, kilonewtons, millimeters, feet, inches, meters, whatever. You want to be consistent. We want newtons, we want meters. In our case, I usually like to do pounds and feet. No, pounds and inches for the other one, but because PSI, right? All that good stuff. And finally, tension and compression will switch the final and initial points. So you don't know what that means yet. I'm gonna explain it. Just relax. But I want you to really remember this kind of stuff, okay? You will need it if you have to verify force for 3D problems. It's really complicated. It took me a while. I had to brush up some stuff too. But you know what? Here's our diagram. Let's go ahead and just continue, right? So here's our diagram. This is our node 1, okay? I'm not gonna label node 1 because it just takes up space. So we have a force beam going this way. I like to make them pretty long. Don't like to just don't like to make them super small because it cramps up everything. These are our beams, right? 4 beams. They're not exactly the way they're drawn, just give or take, right? We found the magnitude, right, of each beam. So let's go ahead and get those. It was force 1, 2, 3, and 4. Again, we use forces, not stresses, because this is a force equilibrium, okay? So force 1 was 320. We don't care if it's negative or positive. We just put 320, the magnitude. 1732. Isn't that the Fetty Wap number? Oh, shit. Next one, 7985. And force 4 is 2734. Okay, I just got these numbers. If you could see it. Got these numbers and threw them in here. Okay, and I ignored the negative signs because they're going to take that into account. We said here compression points into the nodes, tension points away. There's one more we forgot, the 10,000, okay? 10,000. That's the force being applied, remember? Okay, now here's the thing. Compression points in, tension points out. So all of them were compression. Remember, they're all negative, so they're all going into the node. Okay? And this is our x, positive y, positive z, but you won't really need it. Don't confuse yourself. You might think, oh, there's a negative x direction. I'm gonna put negative 2734. No, just relax. This is only for 3D problems. It works, that's what matters. And if you wanna get an A on your exam, you're gonna have to follow this method, unless you came up with your own, right? But, okay, let's continue. 10,000, it's being applied negative, right? This one's given, okay? So that one's already like off the bat, cool. Here's what's gonna happen. So we're gonna take into account every single force. You won't have to, but let's just go ahead and do it just so because you're learning, you know? And even me, even if I already know how to do this stuff, I would still just wanna take it easy and just follow this method. So let's do the first one, 320, we write that down. You multiply it by an angle, but I told you we're not using angles. We're gonna do this. In this case, because it's pointing into the node, we're gonna start at the node 1, go to 2. So you remember how we did the lengths here? It was final minus initial, nodes 2 minus node 1. That doesn't apply here. Okay, this is totally different. So we're pointing at node 1, so we're going to start at node 1. This is our final position, okay? What's the coordinates? So we're at 4 here for the x direction, right? We're doing some of the forces in the x direction. And then, let me go ahead and move that up. And we're going to 0. So 4 minus 0, that's 4. 4 divided by the length, right? You remember hypotenuse, just like we did here, the length, that's all we're doing. Length 1 is 5. So that's that one, okay? Next one, plus 1732. Next one, the length of element 2 is 5. So we're going to put 5. Now, we're pointing into node 1, so we're going to start at node 1 again. 4, the x coordinate, we're still on the x, we're not going to y yet. 4 minus 0, that's another 4 right here. Okay, cool. Next one, 7985. What's this one? The length of the bar is 4, right? Element 3 now. This is element 1, 2, 3, 4. Element 3, the length is 4, so we divide it by 4. Now the x component is 4. It's pointing into the node, so we start at 1 again. 4 minus 4, that's 0. So this one's going to go away. There's no force in the x direction for element 3. Finally, plus 2734. Again, it's plus. You might see, oh look, it's going in the negative x direction, no? And I'll be like, yeah, it is, but our method already takes that into account. Just chill, do it my way, okay? No offense. Okay, so the x direction is 8 minus 4, okay? So that is a positive, well, actually, hold on. It's pointing, we start at node 1. You see, I was already messing up. We start at node 1, so we start at 4 minus 8. It's negative 4. Divided by the length of element 4, that's 6.71. Boom, that's the direction of the cosine. And that's all it is. If we do the math, and all that should be equal to 0, okay? Because we're verifying force, so all this should be equal to 0. If it is, that means we're doing it right, okay? 320 times 4 over 5, that is 256. The next one, 1732 times 4 over 5, that is 1386. Next one is 0, right? 0 over 4 times this, 0. And then finally, this is a negative 4 times this divided by that. That is negative 1630. If you do that, it should be equal to 0. 0, it's approximately equal to 12. This number is going to give you 12, which is close to 0, right? We're dealing with thousands here. That's pretty close. That's just rounding errors. So yeah, some of the forces in the x direction is done. Some of the forces in the y direction should be equal to 0. And that's going to be equal to, same thing, right? 320. Now we're going to do the y components. It's pointing into node 1, so we start at 4 in the y component. 4 minus 4, that's 0. Over the hypotenuse is 5. Next one, plus 1732. Actually, I think it might have been 1738 now that I think about it for Fetty Wap, but it's been a while. I'm old. 1732, it's pointing into the node, so we're starting at 1. The y component is 4 minus 4. That's 0 over 5. Okay. Let's go ahead and do it here. Plus 7985. That's what? This one. Okay, it's pointing into the node, so we start at 1. 4 minus 0. That's 4. And then divided by the hypotenuse. That is 4, right? Of element 3, it's 4. Bracket it up, plus 2734. Okay. That's going to be, it's pointing into the node, so we start at 1. 4, the y component, minus negative 1, that's a positive 5, divided by 6.71. And then finally, minus 10,000. Now I know what you're going to say. Hey, we've been taking into account the positive numbers. Yeah, but it's not pointing into the node. Okay, so let me explain this real quick. So let's say this wasn't a force being applied. Okay, let's say this was another fixed support. Okay, and it was in the same x direction, same y direction. Nothing changed. It just went down to, let's say, 1 unit for simplicity's sake. Okay, let's say this coordinate is 4, 4, 2. Okay, let's say if you would have done it the way I was doing it, and in this case, right, so you know how I told you if it points into the node, we start at that node. This one, it's pointing away from the node. So just start where it's pointing into. So in this case, it would have been this node, right? 4, 4, 2. Assuming this was, right, as an example. So now you would have done this, the what do you call it? Hold on. Oh shit, my bad. It wouldn't have been 4, 4, 2. It would have been, it's in the y direction. Remember, we're just moving it down. I thought it was up and down was z. So this is actually 3, 3. This is our hypothetical example, okay? So let's say the x and z direction were the same, 4 and 3, 4 and 3, but only went down 1 unit in the y direction, like it's saying here. Now, if you would have done that, it's pointing to node whatever, right? It's pointing into this coordinate. So it would have been 3 minus 4. That's a -1. And yeah, this would have been positive just like we've been doing for all of them, right? But that would have changed it to negative, and that would have just corrected the sign, okay? Personally, it's up to you how you do it. In this case, they gave us -10,000 in the y direction, so I just left it like that. And it's not really a beam, it's just a force being applied, so you really can't do it here. But just FYI, that's kind of what I'm saying. Tension and compression will switch the final and initial points. So in this case, all of them have been compression, so we've been starting at node 1. But if this was a tension value, kind of like it's going here, it would have been, the final and initial would have been here. The initial, final would have been here, subtracted from that one. Does that make sense? So you know how all of them we've been doing 1 minus the 2, 1 minus 3, 1 minus 4, 1 minus 5. This case, it would have been this node minus 1, not the other way around, because it's pointing away. I hope that makes sense. But that's kind of what I mean here. Tension and compression will switch the final and initial points. But this case, right, like I said, they just gave us a -10,000, so we're good. If you do the math, 0, hopefully I didn't confuse you guys with this example that I did. I wanted to kind of show you guys that it matters if it's tension or in compression. Now, in this case, like I said, we already know it's pointing down. It's -10,000, right? But I just want to make sure you understood that example. If you didn't, then, I mean, I really can't explain it anywhere, any other method. So it's 0, 0 plus 7985, right? That's just 1. And then plus, what is that? It's 2037 if you do the math. Minus 10,000. That's going to give you 0 is approximately equal to 22. That's pretty close, right? Just rounding errors. And then finally, force in the z direction is equal to 0. So let's go ahead and do that. 320. Now let's do the z components. It's pointing into node 1, so we start at z. 3 minus 0. That is 3 over 5. I'm going to kind of speed it up a little bit. 1732, it's pointing into node 1, so it's 3 minus 6, -3 over 5. The lengths are respective to each one, okay, just FYI, you gotta remember. Let's go ahead, what's the next one? So it's plus 7985, and that's gonna be, it's pointing into node 1, so we start at node 1. 3 minus 3, that's 0, over 4. And then finally, plus 2734 times, what is it? 3, it's pointing into node 1. 3 minus 1. So that's a positive 2 over 6.71. We're done with this paper. So we can go ahead and solve it, right? 0 is equal to, what is it, 192 for the first one, minus 1039, that's 0, plus 815. If you do the math, 0 is approximately equal to -32, and yeah, that checks out. That's pretty close. It's just rounding errors. But yeah, hopefully you understood it. I'm gonna cut the video here. It's pretty long already, but that's the bottom, top. Nothing here. Let's see. This is the top, bottom. We got top and bottom.